Reza is joining
yeah.
in a bit as well. By the way, best first slide ever.
Yeah, I really like
yeah, I found this GIF, so I just made sure to embed it in the context, especially of last week's presentation. You guys can see this, yeah?
Yeah.
Good, full screen.
I see it,
Yeah, so I guess I called it Sheaves forcing and other consequences of an inaccessibly infinite world. Kind of trying to make a call out to last week with talking about cardinals, ordinals, and all of that stuff. I think we'll see pretty quick how they're related to each other. Okay, so it's kind of divided, I guess, into 5 parts. I don't know if we'll actually get through all of this today, because some of it's quite dense.
Right,
but
I only have an hour and a half.
Yeah. So we can maybe cut it into 2 or something, especially since we had WhatsApp issues before. We want to start with kind of going through the connections of topology and phenomenology in the context of what Badiou, and I guess we remind ourselves why we're interested in topology at all, right? Then we'll go through, after that, we'll go through hopefully a visual and more intuitive definition of sheaves. I know we've covered them before, but we'll go through that for a while. Then we have the logic of sheaves of structures, like how do you sort of build models on top of sheaves, or as sheaves as models of like certain theories. And then we'll get to the model theoretic forcing stuff, which is very, very dense. So we can kind of gloss over most of it, but hopefully get the conceptual pieces out. And then some connections with some Badiou stuff at the end. Yeah. Oh, wait a second. Let's go. Here, okay. So I want to start with, this is a couple quotes from Aristotle's Physics, which was in that Renee Tom article I sent you. So this is just, I guess, to motivate about questions of topology, which we remember has to do with ideas of boundary, interior, and parts and whole, right? So let me just read from Aristotle. We ought to try to make our investigation such as will render an account of place and will not only solve the difficulties connected with it, but will also show that the attributes supposed to belong to it do really belong to it, and further will make clear the cause and the trouble and the difficulties about it. When what surrounds then is not separate from the thing, but is in continuity with it, right? That's already very topological there. The thing is said to be in what surrounds it, not in the sense of in place, but as a part of a whole. And when the thing is separate or in contact, it is immediately in the inner surface of the surrounding body. But the surface is neither part of it, of what is in it, nor yet greater than its extension, but equal to it. For the extremities of things which touch are coincident. So I think here, right, we already have that there's some notion of object, which is more topological in the sense that it's like fuzzy, and especially this last part about how the thing that's in it and the surface are neither completely a part of it, but also neither completely separate from it, but are equal to it itself and all parts of it at the same time. So, right, Aristotle is already thinking about this stuff, but then topology itself kind of generalizes all of this, right? It says, I have some sets. I'm gonna choose this notion of something called an open set. I'll say when I first saw what like an open set is, it wasn't very intuitive, besides like thinking of it like in the real numbers as like whatever, a ball or something that you can kind of always approach the boundary forever in some intuitive way in an open set. But I think more specifically, right, it's the importance of this choice of open sets is that it gives it a structure of nearness without measure, right? So there's not an explicit measure on the space in order for it to have a topology. We can have like whatever the space of, we can talk about the space of commodities. Each object within the space of commodities, we don't think of as like an individual point, but as some fuzzy set, right? Let's say it's like a car. There are many ways that you could perturb or change the production cycle and like how you actually make a car such that it's still a car, right? So it's a continuous notion. It seems that this notion of open set is sort of more analogous to what we think about an object when we say something like, I don't know, a commodity or anything like that, than like an individual set-like point thing, right? So I say, a topology is a structure of nearness without measure, which coincides well with how phenomena appear as amorphous blobs that we sometimes can and sometimes cannot put a measure to, whose boundaries, interiors, and parts are something we can coherently talk about. So when, right, if the world was finite, which I think some people might disagree with us saying it's infinite and would say it's finite, you could literally list out all the ways that you could slice the world. And then you can just have a list of every single part that is within the topology and just accept everything, and that would kind of be the end of it. But if we contend that the world is infinite, it becomes very difficult because of questions of like the continuum hypothesis, right? Even the notion of if you have an infinite set, even just the natural numbers, it can be the smallest infinity. The size of its power set is not stable in like all models necessarily. So there's always, whenever you're in these, if we're gonna take sort of as a base, I guess like axiom of faith that the world is infinite and that all objects are inherently infinite in that they could continuously change in a whole bunch of ways and still be that same object, then the space of just about any world is also infinite, and thus the size of its what Badiou being an event calls the state of the situation, right, is always going to be inaccessible. This is something he agrees with us as well. So then what that means is that the choice of topology in an infinite world is very important, right? There can be anything from the simplest, where the open sets are just the real numbers and nothing, in which case you're not differentiating anything. Or you could do the extreme where every single set is open and then suddenly the topology isn't saying anything about the structure of the world, but just taking the world sort of as a pure, like undifferentiated set with no internal structure. Yeah, I don't know if Dennis, you have anything to add if that makes sense.
Yeah, no, that's a perfect introduction to it. And I was thinking what you're saying, the concept of boundary is also really important, because we can think of open sets as just regular sets where you remove the boundary points, and then because one of the possible definitions of an open set is that its complement is closed. So it's like you have just the interior without the boundary of something, and then you can ask the question of like, okay, but then what are these boundary points that are being removed, right? Like why in a given production process, like you mentioned, or some kind of thing that you're trying to topologize, like what are the boundaries that you're trying to like forget in some sense? Because yeah, I don't think like when we say infinite, usually we have in mind like something really big, but it can also just be something really small, but with the boundaries excluded.
Yeah, so that I think also gets us into kind of this example with the ship of Theseus I just wanted to mention. But first on the left, we see here, just to remember in set theory and standardly, right, the logic is classical in the sense that belonging, right, the basic operation is belonging, either for some set X, either it's in some set, some other given set, or it's not in the set. There's no in between. There's no like fuzziness here. But from the topological perspective, right, where your base notion is an open set, and seeing whether one open set is a subset of another one is not just yes or no proposition, right? You could have it be completely a subset, okay, then completely yes, sure. Or you can have it be completely not a subset, or you can have some intersection which is non-trivial. So these objects in general seem, and especially when we think of parts of objects, it's usually important to keep in mind their intersection and whatnot, and not think of things only as individual things composed within sets, right? So in this context, we can kind of, I think, reimagine the classic from the ship of Theseus question, which is basically after how many replacements of the ship, of parts of it, is it like the same one as before? So I guess like the topologist response is that outside of some context here, context meaning some topology of the space, the question is really kind of incoherent, right? So like in the context of, for example, a museum maybe that like found Theseus's ship after he died sometime and is trying to preserve it and explain the context of whatever his life, blah, 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 blah. The individual parts of it might matter quite a lot. Whereas for like the actual sailor, whatever, Theseus himself, it would not, he would probably replace things as long as it worked for him, right? The ship doesn't have the same sort of, I guess, like almost sentimental value that maybe in the context of a museum or something else it might have. So these different contexts give different topologies of the space that give us different differences that make a difference, right? So a topology in a way is a way to keep track of differences that make a difference, in the sense that it tracks nearness, right? And if two things are both in the same open set, then they are in some senses, right, they can be said to be near each other. So this is going to come back a lot. And yeah, the really important notion here is that the structure of which parts of the situation count, both will determine the logic of the entire situation, right? The topology itself determines the logic and is also dependent on the context, right? So it's dependent on whatever the given context or topology of the space that we're starting with. Yeah, should we keep going? Make sense? Topology, everyone buys it. So after last week, I think there was a little, I know Reza's not here, but I heard there's a little bit of like maybe some confusion over, I think, Badiou's notion of the ontologist and the inhabitant.
Yeah.
And I think that this sort of topological point of view gives us some insight, right? So the ontologist sort of, sees a situation from the outside. It's almost like, it feels, I don't know if this is exactly analogous, but it feels like the role of something like a historian, right? Looking at the fact, at whatever, the event after the fact. Kind of like once already everything's known, and they sort of by definition cannot be strictly within the situation. So, I mean, mathematically speaking, this is like looking at some surface, like a torus, for example, from the outside, which from some outside embedded space, right? So this would be looking at like a surface, like a torus, as like a donut, rather than looking at it from the inside where, right, the sides are glued. I have an image of this later. Actually, if I can show you guys really quick. Here, it's this image. On the left here, the one that says stretched underneath is kind of like the topologist from seeing this space, oh, sorry, the ontologist, seeing the space from the outside and not from within, right? So from the outside, there's actually some distortions of the space. It sort of looks like it's curved. And in a sense, it is in one direction, even though the space, the entire space itself is flat, meaning that it's really just a folding of this flat Euclidean space here. But then the inhabitant is sort of like on this right side or in the middle picture. They live within the space and they might not necessarily see these boundaries and know that they're connected up until they like do some experiment that can figure out this global connection that they can go around and get back to the same place. The ontologist obviously can see that right away, but it's always conditioned as being within some other context. So the inhabitant, right, otherwise is, on the other hand, is within the situation and always only sees what is like locally accessible, aka what is within some open set around where they reside. And I think this will be a really good perspective for the rest of this talk to keep in mind, because the Sheaves perspective is sort of like an inhabitant perspective. It's how, for each one of these sets, how do we construct a structure that respects certain conditions? Any questions?
This makes perfect sense to me.
Yeah.
Yeah, I always like this idea of it's like the ontologist is like the Euler description of like an invariant, and the inhabitant is more like Jordan theorems kind of thing, like paths you can take on some, like from local to local, but it tells you something about the global from inside, right?
Yeah. Okay, I'm just gonna keep going. So I just wanted to mention this one last thing that we want to really make sure to keep in mind that to think of the topological spaces here as lattices, right? So we think as some lattice of sets that have the inclusion relations, and that each element of the lattice, rather than thinking of it as like some point or rather some random post set, it's going to be actually an open set. One reason for this perspective is usually when we think about lattices, we think about finite ones, at least intuitively, but they can be super infinite, right? Like they can have ordinals within them, like in each, even in each line, like there's nothing that's preventing things like that. In fact, there's, I believe, what's his name? John Conway's construction of the, what's it called? The hyperreals?
Surreal numbers.
Or the surreal numbers, yeah, is basically doing this. It's like a bunch of ordinals on post sets, and you can construct things much, much further than the real numbers, both infinitesimals and big infinities. When we think about the topology, right, as a space of lattice of parts, right, another thing to keep in mind is that it's looking at it as a Heyting algebra, which we remember is a model for the structural rules of intuitionistic logic. So it doesn't need to satisfy the law of the excluded middle. But we always want to think of it as like an embedding within the greater power set, right? The power set is this big, inaccessible. We always want to think about it as this inaccessible thing because it's always too large to sort of enumerate constructively. So by thinking of the Heyting algebra as almost like a more tractable, almost like approximation of it. This is it's just a good perspective to have when we start talking about sheaves and things. And then once we start constructing the sheaves, they're basically constructed in a natural way, aka respecting the inherent structure of a topological space. And it's because of this that the geometry actually ends up informing the logic. And this is like essentially straight out of the atomic logic of Badiou, but in a more general sense. And hopefully a little bit more intuitive. And enforcing the conditions, this is kind of on the bottom right. This is a little bit of a quick summary of what the technical aspects of, at least from this paper, are. That forcing a set of conditions on some classical structure, right? So if we want to force something on ZFC, for example, adding more sets to the power set of the natural numbers so that we get the continuum hypothesis to not be true in some model. So we take first the classical model, then we expand the classical structure into an intuitionistic one. And this usually involves, this is something we'll mention briefly, the double negation topology by basically replacing everything with the double negation. And because the rules of double negation, when you apply them to any Boolean algebra, end up becoming a Heyting algebra, then you get this intuitionistic structure. And at the end, you sort of glue everything back along a generic filter. And then this gives you this forced classical model from the previous one. And that's not the only universal way to do it, but it's sort of the general structure of how it usually happens.
My view on this is that this lattice structure is why we can, because both topological spaces and logical propositions share a lattice structure, we're able to kind of jump between the two to do this, to perform this kind of it's like a shift of perspective, but which operates around this lattice. So on the one hand, you can choose a topology as a series of inclusions, right? As this partially ordered set of inclusions of parts of the space, but also with propositions, you can connect them via how one proposition allows you to say about other propositions, right? Or allows you what not to say as well, right? Because if you affirm one proposition, it excludes a bunch of other ones because those other ones would be contradictory with the one that you affirmed. So both share this lattice structure, and so this whole forcing over sheaves and everything it's all about trying to think both of these lattices together, and in this infinite way where it's not clear how the global structure of things is laid out, and so like you're very much taking this position of the inhabitant, because you can't really trust that you know the entire structure of this topology, but you can cleverly, if you know certain rules and tricks, you can cleverly design a way to talk about this this extra thing you're adding.
One thing just I want to ask you guys before we move on to more complicated stuff is that, I mean, we mentioned last time, and it's something it's like just a cool to realize that with set theory, you get a sort of division of a concept that usually we thought as being one. Like there's something about numbers that suddenly becomes split into ordinals and cardinals. And those two things have different information, and moving between the two allows you to say things you couldn't say directly by just keeping with the ordinals, for example. So, but that split is kind of the split between order and measure. Cardinals with measure, order with ordinals, right? Of course, they are, for natural numbers and so on, they have a certain type of total ordering and so on. But it's interesting that the way that the move from like topology, the way topology splits open sets from measures and associates open sets to lattices on the one hand, right? So there's an ordering of open sets, but that's not the same as a measure. It seems like a analogous split of a constant. Like I can talk about which is, I mean, when I try to dazzle somebody with philosophy of mathematics 101, I talk about this. Oh, isn't it amazing that set theory splits these two aspects that usually think of them as the same, and that has something to do with the infinite. In the infinite, this split becomes very clear. It seems like the similar sort of counterintuitive intuition that is at the bottom of everything is a similar thing that open sets require you to do. Suddenly, you're allowed to talk about order going in a kind of bifurcation with regards to measure, right? And then you can move between the two and get information, new information out of it, right? It's no longer, and again, infinity plays a part in seeing how the two things really get split and not, it's just not a way of speaking, right? Because
yeah, it is.
It's really profound that you can.
Yeah, it's definitely something like an order on a choice of subsets, which gives you, what it gives you, and this is an important thing, is it's like the structure of the world from the perspective of an inhabitant, right? So if the topology was simply trivial, then nothing would be differentiated, right? Like everything would be one. And if you have, on the other hand, where everything's open, then everything gets individually atomized, right? And it's just the individual, like each individual point is open, and then therefore everything's open, right? And then, so then you in both extremes, right, you have essentially no information. So it's important that it's one connection, right, that I think is important, is that because it's intuitionistic, it has a really deep connection with like constructive logic. So the perspective of the inhabitant is always one that is like, is constructive from the place that they are. It's going to construct something on top of it, rather than just like prove the existence in some like globally that something does or doesn't exist. So yeah, I think that's a really good perspective on why topological spaces are kind of important. And it's an unintuitive notion, and it's one that takes a while to get used to, especially when you think about like its place without measure. Like how do you, especially once you have like something like the real numbers, right, that's already enumerated, like how the hell can this thing be like have a structure of which sets, or how the sets like are glued together without having an explicit measure on it, is like kind of an unintuitive thing, but it works because these sets are infinite, because of the rules of how they glue together. Yeah. Okay, let's go on to Sheaves. This is kind of the fun visual part. So hopefully we can just spend maybe the rest of the time on this, possibly. We'll see. So the idea of Sheaves, right, is kind of motivated by, originally was fiber bundles, which is the picture kind of on the left over here. So a fiber bundle is basically when you take some base space and you put something on top of it, right? So at each point you put whatever, a bunch of things, right? Here, there's 4 points. Each point has 6 points above it. Okay, a very boring fiber bundle, but it's something, right? You have the reason why, and we should go through all these terms because we're going to use them and they're kind of confusing at first. But so the stalk, right? We think of it literally like a stalk of grain, is the thing that is above the space, right? And to motivate fiber spaces, and they're very important in a lot of physics and other things, is, for example, like a tangent space, right? So if you have some surface, imagine like a circle, at each point you have the tangent space at the point, which is a vector space that's attached to the point, which is where things like the velocity arrow lives, right? So whenever you say that an object is here moving at this speed, what you're saying is I have this point here, and then this element of the tangent space And the tangent space has certain properties, how it moves around, and that determines like the differential structure of the space. So a sheaf is sort of a generalization of this idea of a fiber bundle, where you have above every point, right, you have some object. But here, instead of your base space just being some whatever arbitrary set, and instead of each one of the fibers being often the same thing, at least simple fiber bundles, usually you just put the same thing over, for example, tangent space, usually it's like that. But a sheaf kind of topologizes it in the sense that above each point, right, you have a set of things, but the set of things has to respect the topological structure of the space. So we see here we have A, B. A is this big left set, and B has this big right set, right? A or B, which is the combination of them, should have just the middle one, and then the A and B is going to be the whole thing. That, like this flipping here, is the contravariance of it, but we'll talk about that. But the notion of the basic idea is it's attaching structure in a way that sort of respects the topology of the space. And I have this image here still. So they formalize, right? So this is kind of conceptual. They formalize the idea of a collection of things that can vary depending on where you are, right? And where you are here is not going to be a specific point. It's not going to be, I'm just here in space, but where you are is somewhere within the topological space. So you're in some open set. So right, as I said, the data that you attach should respect the structure of the topology. So the topology is sort of what's given. It is the world for the inhabitant. So a set itself, and we'll mention this also later, can be thought of as a sheaf over a single point. So you can, any set, right, you can imagine here, you can just put any unstructured set, put as many things as you want on top of it. In a sense that generalizes all of set theory. Just you take one thing and then you can take multiples and repeats of that thing. But that's sort of like the degenerate case. It's not very interesting. But generally, right, a sheaf is much more interesting because you have not just these structures, right, that are above each individual point, but the way that they interact above the points will usually be pretty non-trivial. So the sheaf carries a structure which varies over a base topological space. The structure varies across the base space such that it respects the topology. In other words, it's a sort of continuous functor. This is one, I think, the simplest way that I like to think about it is, or maybe a continuous pre-sheaf, if you want to call it, but it's sort of generalizes the notion of continuity, not just for a function, but for a function in general on any category. An intuitive example of this is something like sets in time that you can just continuously vary over, but they're we'll get into hopefully more examples. Make a little bit of sense?
Yeah.
Okay, let's continue. Yeah. Okay, so this is the actual topological definition on the left here. So all a topological, a sheaf over a topological space will be is just going to be a couple X. And one thing I want to know is that when you see the definition of sheaves, there's going to be two different ways you see it. One is this sort of topological way in which the arrow from the sheaf is kind of going in opposite. So here we see the arrow goes, here the arrow goes down. So this arrow, this is the sort of topological arrow definition. So this is like the definition of a sheaf as something like a cover, right? So we have this complicated space up here, and I project it down to the simpler space. So each one of these gets projected to the simpler space. Okay. A fiber will be just the complete inverse, where I take the point and I just get the set of all the things above it. So the fiber basically gives you this like stalk thing. Then a section, right, is going to be something that locally is like this fiber. So what that ends up being is something that is like literally like a cross section that cuts across this. Can you guys see my mouse moving around? It cuts across this way.
Yeah.
So, right, so remember the terms we're going to have. Stalk is this. Fiber is the actual function that gives you the stalk. A section is a choice going this way, and the sections are going to be our general notion of an object. A sheaf will be like a structure, and a section will be like an object on that structure. And these germs are these individual places in which, there's a reason why they're called germs, that comes from algebraic geometry, where these stalks are glued together at a point. But I just went back to point that out, but that this arrow here, right? So in the first definition of a sheaf, it's just going to be a couple, it's basically a cover. It's going to be some base space X, and then this function, this functor E, this other space E, and the functor P, where E is also a topological space. And this functor E is a local homeomorphism, which means that for each one of these, so this is up here will be E, and on the bottom is the P. So for each one of these points up here, actually, let me go up here. For each one of these points up here, wait, sorry, 1 second. This thing being a local homeomorphism, yeah, it means for each point in E, there's going to be some open set around it, such that this map here, down and then back, is a homeomorphism, which means that it looks topologically the same. So what that means is that the sheaf is basically locally modeling your space at every point, but in a bunch of different ways. So
yeah, similar to the chart and manifold thing, right? Like if you look closely at a manifold, local parts of it, local slices of it are flat, like a Euclidean space. But then if you zoom out, the whole thing can be some crazy thing you can't even imagine, right? So that's what this condition number 2 says. Condition number 2 just says if you restrict your function to V, a local subset, then you get this flat structure again. You get this not necessarily Euclidean, but just this like you were saying, homeomorphic structure, which makes it, some kind of familiar structure, but it doesn't require that the whole has that structure. That's the interesting thing. It's like you have two objects locally, they look the exact same, but if you were to zoom out, one of them looks totally different, can look totally different than the other.
Yeah. One good way of thinking about this is that at each point, right, in the sheaf, so in the structure that is on top of the base space, at each point there, locally, it looks the same as the base space, locally. Yeah. So it basically, in whatever it maps to, it ends up being homeomorphic to it. So it's a local mapping of the base space, but adding additional structure. I think the good, I think we mentioned this later, the good example to keep in mind, this is from the Benavides paper, is thinking of causal structures as a sheaf over spatiotemporal states. Okay, so that is, recall here, so it would be like on the bottom, this is like for example, like the manifold of the universe. It's all sets of whatever locations and times that are valid, right? And then above it, we have basically the causal structure, where you have different things affecting one another. And then for each point in the causal structure, you have like a light cone, both forward and backward, of all the things that could possibly have caused that point, and all things that could possibly cause it in the future. So then you can think of, like the causal structure of the universe as a sheaf on top of whatever the manifold of the universe itself. Just means like the space of the universe.
Gotta love when people go to like the explanation of causality in general to explain to explain the mathematical concept, which is more complicated than that.
Anyway,
a simple example is
a simple example would be the causality.
The universe is a very simple example. Yeah. I think it's a good motivating example.
No, I totally
and then so this definition on the right, well, notice, so the left one, right, is this like topological definition, which all it's saying is that a sheaf is something that is basically a local homeomorphism, right? That each point in this sheaf space, it locally looks like some local area of the base space. This other one kind of goes in the opposite direction, right? So rather than the base space being X, as on the left, here the base space is this O here, right? This is like the lattice of open sets, where now it's a pre-sheaf that's going to take for each open set, it's going to have above it a bunch of things that are attached. So the set is exactly what that. So it's for each open set, you have a set of usually functions or something that are glued together in a certain way. In order for it to be this pre-sheaf, which remember basically just has to restrict to sub-objects, and that's the main condition. It'll be a sheaf if it's for all open covers, the set f of u is an equalizer of the pair functions. So this basically is just going to say that you can restrict from either one of these places, and it should be the same. So I think the one on the right is kind of a less intuitive definition than the one on the left. At least once you kind of understand what's going on with topological space and whatnot. Dennis, do you have anything to add to this?
Yeah, and I agree. It's definitely less intuitive. I think the interesting thing, maybe just we don't need to try to understand it completely, but maybe just thinking about how the gluing condition of a sheaf is captured by this equalizer limit thing, because we want to be able to add an additional condition on pre-sheaves that if you find two open sets that overlap, then you should be able to glue along those open sets to produce a bigger chunk of the pre.
Oh no!
Yeah.
Just saw the Gabriel's message.
Gabriel's message.
I understand. We just got 2 kittens. So they're sleeping behind me. Wait for him to come back.
Yeah, our dog recently puked and then ate the puke.
Oh no.
Yeah, and we were too slow. We were too slow to stop her.
Oh no.
Yeah, sorry for that gross image, but but anyway, for this limit, I'm really interested in understanding that this limit definition, because it implies like there can be many pre-sheaves that kind of there can be many pre-sheaves that do similar things in terms of they obey like the restriction condition, but they don't assemble quite correctly, right, into a sheaf. Like they don't glue uniquely. I'm kind of interested in that idea.
Yeah, there's a great example from we should wait for Gabriel, but I can just go. There's a great example from complex analysis of this, where the sheaf of the pre-sheaf of bounded holomorphic functions, right? Holomorphic just meaning basically differentiable for complex. Is good enough to know. But the pre-sheaf that takes just bounded complex functions, right? So it takes, for each open set, it just gives you all the bounded and holomorphic functions on it, is not a sheaf because of this theorem that any bounded function on the entire complex plane is constant, which is kind of crazy, which is saying that any bounded function that's continuous or that is differentiable, or sorry, any function on the entire complex plane that's differentiable will basically go to infinity somewhere. But because of that, a very classic example of bounded, the sheaf of bounded functions is not, or pre-sheaf of bounded functions is not a sheaf.
Oh, it's interesting. Yeah, I need to look that up.
Yeah, there's a lot of, it's because of Louisville's theorem. It gets very deep into complex analysis things, but I think on the Wikipedia page there's a whole section of like pre-sheaves or not sheaves. You're back. Dealt with the dog.
Dealt with the dog's vomit. Yes, in my car.
Okay. Oi. Okay, let's look at this. I just added these as Reza I saw. I guess Reza had a couple more things on his left. We can get back to that.
I can do it in next week. No problem.
Yeah, we can do that. But I just added these two images here. This is the same definition as examples of sheaves from geometry, which are covering spaces. So here, right, the sheaf will be the structure on top of the surface, right? So the base space in this case is actually the surface itself. And the structure on top of it is this covering space. So in both of these situations, these are what's called the universal covering space, which means that you can basically make any type of, in this lowercase, two-hold torus out of this sort of weird tessellation. So this is actually, even though it doesn't look like a tessellation, this is a tessellation. Oh, this is a tessellation of, is that just my things? Oh, okay, this is a tessellation of hyperbolic space. So these are all hyperbolic octagons. Octagons, yeah, that are all the same. There, my slides are freaking out. There you go. So each one of these is actually the same. And the sheaf here, right, is going to take each point in the surface space to all of the points that it corresponds to here. So for example, in the torus up here, the sheaf takes this guy who, these are both the same, right? This is just when you glue the red and the blue, it's this space. So the sheaf is going to take this guy to all of the places that he corresponds to in the unfolding of the covering, right? So this is the covering space, meaning that if you go the other way, this is how you form the quotient. And here the same thing. You have right above each point, you have a point inside each one of these domains you have a point inside of each one of these domains, and the functions on it also respect this, right? So it's going to be, a local homomorphism, which means that for any point in this space here, I can choose an open set that's small enough, right? As long as it doesn't like cross over and go behind or something. I can always find one that's small enough such that it'll fit here and be homomorphic. So these are kind of like some easy starting examples to start having things visualized. So here we see the same thing. Yeah, does this make sense?
Mm-hmm.
A little bit to visualize the structure on top of some basics. So another way, oh, I didn't really completely finish this. That's okay. Another way that we can think about sheaves is sheaves over graphs, right? So here, this is an example of a sheaf over a graph where for each node, you attach some vector space. Here, these are all different vector spaces. And for each vertex, you also attach a vector space such that the maps you have, oh, sorry. The edges are, oh yeah, they're all vector spaces, and for both the vertices and the edges, along with maps between the vector spaces to here. So then the section on this sheaf ends up being a choice of a bunch of vectors here, such that they respect all of these maps that we have. So I plug in the vector here, and I get it. I put it through this map, and then I end up getting the same vector that I chose for here. So they should all sort of respect the structure. So here we can see it's a graph, and it has a structure on top of it where each node is a vector space, but the vector spaces are mutually compatible based on their gluing. And I like this quote. This is from Benavides, that in agricultural terminology, right, a sheaf is a collection of stalks of grain bound together by twine. In mathematical terminology, a sheaf is a collection of stalks of data, right? So each one of these things, these like vector spaces here, is a stalk of data bound together by linear maps. Where here, linear maps really means linear maps in the context of this particular example. But in general, right, if you have some other structure, it doesn't have to be linear maps. It could be whatever maps respect that structure and are natural to that structure. Yeah. Okay, here, this is kind of the example about causal states and spatiotemporal states from the Benavides text. I thought was quite good. Which this image, right, shows. It shows kind of the intuition that on the bottom we have sort of the space of the universe, and above each point, a spatiotemporal state, which is a location and a time, we could have many observers intersect at this one point. And the observers here are going to be thought of as the sections, which are either, depending on how we take the sections over this base space, right? If the observers vary over time, so that's like within the light cone, then that's going to be a time-like observer. And if they vary like crossing between light cones, going faster than light, or going in some perspectives, right, in the reverse of time, and that's a light-like, or sorry, space-like observer. So I think it's a cool example because it shows how you can have, right, this structure on the bottom, which is space, which is the base structure for gluing together all of the local instantiations of causal structures, right? So local causal structures are, I have a, whatever, the limit of it is my light cone behind me and in front of me. I have things that possibly caused me and things that I possibly caused, right? But my light cone and your light cone and everyone else's all intersect in such a way. And when we sort of intersect them all together, that is going to be the structure on top. It's something that's both, it can allow us to think of it as on top of, built on top of space, but also as sort of slicing it by the constraints of the space itself, right? The constraints being whatever, special relativity, quantum mechanics, all whatnot.
Yeah, it's like it's useful in general relativity because it's you basically think of like, if you think of all possible observers in the universe, like if you choose any two of those observers, they're not going to agree on what's actually happening causally, because of the complexity of this manifold and their relative velocities and so on. But if you find a local enough fragment between two observers, they can agree, right? So these observers, because they lie above the same neighborhood of X, they all agree on what's happening. So we can take that topological structure, and actually we can infer the topological structure from the points of agreement as well. So if two observers agree, we can say they are in the same neighborhood, right? So actually it can go both ways, right? If we know the topology, we can say these two observers must agree because they're local to each other. But if we know that two observers agree, we can also say that they're local. And that actually gets weird, right, with entanglement and all that weird quantum stuff, because you can say like, well, they're not, sometimes two things are not local to each other, but they do agree on some information. So I mean, I don't know anything about that, but it's another example of how like topology can inform the propositions we're able to make, and propositions can also inform the topology of the space.
Yeah, and I think this quote, just to go through this again, just to remind ourselves, is good to go through. So this is a sheaf F on X can be described as a rule which assigns, right, at each point of the space, a set Fx consisting of the, what they call germs, which are the individual data that you're pasting, to be considered as defined in neighborhoods of the point X. So this is the really important thing, is that everything is defined in neighborhoods of X, as Dennis was saying. This is the extensional property of truth for Sheaves. Then the sets F sub X for all X, right, can be pasted together by a suitable topology so as to form a space or bundle projected onto X. Okay, so this is like the pasting together of all the causal spaces. An individual good function, right, for the sheaf is then a cross section of the projection of the bundle. So this is taking, right, for each element in the base space, we're going to choose something from the sheaf, and we do it in such a way that respects the topology. So then viewed in this way, a sheaf F is a set F of X, which varies with a point X over the space big X. So this is the perspective of sheaves as what are called structured variable sets. So they are structured in the sense that they always have a structure which is preserved, which is in this case the topology, but they're variable, so we can describe them how they vary continuously, but being sort of the same object, right? So you can look at like the sheaf as it moves through different points in time, and it helps us, it's ways to keep track of different kinds of objects in the space. The really nice thing about them is that it's, whenever you get right? Whenever you have a sheaf, you never just have one sheaf, right? Because you also have you're automatically given by the topology just by taking subsets. You can always get a subsheaf of the original one, and not just by cutting through the original topology, but you can cut through like the sheaf itself. You can just take individual pieces or whatever. So it's adding quite a lot of structure that it's not like a sheaf is never only concerned. It's not just like one instantiation of something. Because of this topological structure that's very fuzzy, you end up getting, anytime you have one, you have basically a whole family of them already. And you can do things by building up these families over time. Okay, any questions? Sheaves definitions. I don't know how much sense it made.
No, I think it's making a lot of sense.
Yeah.
Yeah,
now we can get
that has been not clear so far.
Mm-hmm. Okay. So here, I guess we want to talk about a little bit of the motivation of the logic of sheaves of structures. So now we have this idea of sheaves, which is kind of like a continuous functor. But now the motivating idea is that we want to localize truth values on propositions such that we can infer new propositions from old ones depending on the topology of the space. So we want to take this structural topological idea of sheaves and we want to see how we can inject basically logic into it. And we'll see that the space itself can be topologized by the valuation of propositions, which will will spell out explicitly soon. So recall from in one of my previous talks, I think we talked about this stuff a little bit, but just in model theory, just what a structure is. Right? A structure is basically, for mathematics, it's kind of like the language plus an interpretation. So it's the syntax plus the semantics, but it's not like, it doesn't, if you just have the syntax and the semantics on its own, there are many, that doesn't give you a completely unique model in and of itself, and we'll see that. But it's basically just a choice of some base set and a set M with interpretations for symbols, which are relations, which a relation you can think of as just a subset of the cross product. It's not the cross product, just the product of however, like an n area relation would be a product of n many of your spaces. It just be some subset of that. Function symbols on it, so which functions are allowed, and constant symbols, which are going to be like your variables and whatnot. And the underlying set M is what you call the universal domain of the structure, or the universe of the structure. Okay, so this is kind of the background. Just basically, we can have this abstract notion where we have a first order language that has symbols, quantifiers, all that stuff, and then we can add relations, functions, constant symbols. So we're gonna take this kind of to the next level by doing sheaves of structures. So a sheaf of structures over topological space X is gonna be a sheaf that has over each point, it has a bunch of these things such that they agree with one another, right? And the basic notion of when we talk about the structure, we're going to say that the sheaf forces a proposition, right, at some point X, if for the sections, right, these sections are going to be the objects of the sheaf. If we can say that there exists a neighborhood of U such that the proposition applies for all points in the neighborhood. So this is the extensional notion of truth, that truth will not be just is something true at a point, but is something true in a neighborhood in which you live. And this gives us the idea of local truth, that, for example, something can be true, right? If it is sort of close to you, for example, in your causal past or future, or if it's like close enough to where you are. Yeah, so then we can continue going, instead of just defining, right, forcing at a point, by allowing, by saying that it's going to be when the proposition is true in a neighborhood of that point, we can say that it's force on the entire open set, which is kind of what we're gonna, the direction we're gonna go with this. If for every single point in it, it's extensionally true in this way. Okay, so this is just basic, basic definitions without too much detail.
Yeah, we're forgetting the points. Basically, we want to get rid of the points and just talk about like forcing over open sets.
Yes. So forcing. So this kind of brings us, I guess, to Kripke models, which end up being a specific situation, a specific subset of models, sheaves of structures in general. But this is we're just going through kind of the basic definition, right? So a Kripke model is going to be over a poset. So this is the basic notion that we're still going to be keeping. For each point in the poset, the stalk over it, which is KP, is going to be a classic T structure. And then this is the important thing, is that for any two elements of the poset, if they're comparable, right? So if one is less than or equal to the other, then there is a homomorphism, right, between these structures. So you can say there's one going from the lower one to the upper one. So it's sort of like embedded within the other one, such that it's going to be the identity for itself, and such that it's also transitive. So the Kripke forcing is when you have this thing of a Kripke model, and then you inductively define how propositions, which are going to be reinterpreted not just as right, symbols and things, but the propositions themselves will be admitted subsets in the situation, right? So the subsets that we see, in a sense, are going to be the subsets such that we can say something about them, right? That we can actually pick out subsets. And you see there's all these technical ways of doing it. We see that, for example, like the relation is going to be forced if and only if, right, you get at some node, and everything is always forced at a node P. So it's forced here. When we think of these node Ps, we think of them as open sets. We're forcing at open sets, right? If and only if this point exists inside. It's kind of the obvious thing. Exists inside. These are the relations that are over P at this point. And the same thing applies for others. In particular, another one to note is that the negation is going to be if and only if for all, right? So we're going to say that P forces not some proposition, if and only if, for all Q greater than P. So everything above our base point has to not force that proposition, right? So it not only does it have to be true at P, but it has to be true at everything above it.
So that picture depicts, and yeah, I mean 3, 4, and 6 for for number 3, 4, and 6, they all have this property that it has to imply something about the future nodes, or the nodes in that are ahead of the current node. Yeah, so this is what I was saying earlier also about the lattice structure of propositions and the lattice structure of open sets, that there's this way to go between the two. Because if you think about it, what we talk about as an ultra filter, that's basically all nodes above a certain node, right? That forms an ultra filter. So we can see that the ultra filter is relevant for forcing.
Yeah, well, that's a point ultra filter, right?
Mhm.
So we still have the generic ones, which are the kind of mysterious. Yeah.
Yeah, that one. Yeah, that's we'll get to that. But yeah, for this one, at least for a simple idea, like you have an ultra filter that starts at a point and then kind of propagates to all future points.
Yeah, so this is just basically to show, right, that this general notion of sheaves of structures includes many of the other model theoretic things. And in fact, this is kind of the use a slightly more general version of a Kripke model, but it's essentially the Kripke model framework. So this is kind of what we can be thinking about as, rather than just a Kripke model in some partial order, it's going to be on an arbitrary topological space. But as we already know, right, a topological space is already kind of a partial order, right? It's just much larger because it's gonna, you can filter things like infinitely. So this is some technical things. We don't have to go through all the specifics at the bottom, but I just wanted to add this because we talked about last week the right, Cohen's forcing with the whole schema of names and everything, right? And it's kind of, I think, confusing and a little bit unmotivated at some points. But this is actually the construction of how you could think of this as a subcase of what we're talking about here, which is sheaves, that Cohen's names are constructible as sheaves. In fact, sheaves kind of end up being one of like the core things in math. It's like you can look at almost any object of importance and like maybe 70% of the time it's secretly some kind of sheaf. But basically, if we can go through here, the idea of this is when you pick a name, remember a name is composed of in another name and an ordinal corresponding to that, right? So it's ordered and it has a condition on it as well, where you take the corresponding sheaf. It's going to be what's called, this is the TLDR, we don't have to go into all the details. It's going to be something called the universal sheaf with a generator at level P for each P tau in sigma, so for each element of the name, with the relations of two things being related, 2 points, 2 names, at level Q less than or equal to both of them, whenever they're forced at this level Q to be equivalent. So this is admittedly one of the things you have to for it to start to click a little bit, you have to stare at it for a really long time.
Yeah.
But the idea is we're taking for a name, we're taking this pre-sheaf, which is defined in this way, okay? Where this thing, P pre-sheaf, is just the pre-sheaf generated by a single element, okay? So all this is on a post set. So think of some partially ordered set. And then it's going to give a value to each thing in the post set. So if for some Q, it's going to be the set, right, containing 0, which is just the set containing the empty set. If Q, right, if the thing you put into it is less than or equal to P, and it's going to be the empty set otherwise. So it's going to, everything below it, it's going to map to this, and everything above or not comparable to it, it's going to just map to the empty set. Okay, so it's kind of like the trivial thing. It's just keeping track, is it less than or is it not? Then what you do is you glue, so this U thing here, this is the direct limit, which is essentially gluing them all together. So I'm going to say, I'm going to take the sigma pre-sheaf is going to take for each element p comma tau in sigma, where p here is in this post set. It's going to basically union all of these like single element pre-sheaves together. And then in order to sheafify it, to make this pre-sheaf thing, which is just taking all the things together, by basically taking this relation that whenever that two things are going to be equivalent at a level Q if they're forced at that level to be the same. So what that does is that ends up taking this thing, which is just a bunch of these pre-sheafs taken together, and it's going to glue them in such a way that you get something that you can still, sorry, 1 second. I have to remind myself. Oh yeah, so this is just trying to think of the names of the sheaf. So when we do this sheafification thing, we end up basically getting an belonging relation that ends up respecting the same thing, and then we can show that all of the properties match up. Which basically, right? And then once we have this, and then we take a section on it, a section on this sheaf, once we sheafify it, ends up being equivalent to actually choosing forced elements of sigma, which is what Cohen's doing. He's adding the forcing. So this is just to say that yes, the names that we talked about before, that's kind of unmotivated, can be thought of in this context. You know, it's complicated, but it is sort of the same thing. Maybe we won't go super. Yeah,
I have to look at that one again. Yeah, it's hard to follow.
Yeah, but I mean, for the vague amateurish analogy is that because Badiou moved from the subsets of this situation to the conditions, and then on the conditions you get the names, right? So the conditions concern, let's say, the partially ordered set. Let's say that's like the sort of lattice-like organization of these parts, right? And the names are the thing where it's like the fibers we're attaching to it with added structure, like the sections and stuff. Is that like vaguely where the analogy goes through? But I mean analogy because it's not what you wrote.
I'm trying to think.
Right, I'm trying to go back to the more visual images you had of the sheaves before.
Yeah, in general, this is one thing I'll say about trying to maybe visualize them. The issue with sheaves, right, is of course there's many examples where you can't visualize it very well, right? Like these surfaces and things and covering spaces is a very easy way to visualize them. But in general, sheaves, especially when you get things that glue in like non-trivial ways, it ends up becoming very quickly almost impossible to really visualize them.
Yeah.
Often, and I don't know if there is really a visualization on this, but here the idea more is that these individual pre-sheaves on each individual thing and we're unioning them all together. Each one of them is just basically this like simple pre-sheaf that's indexing one specific point in the post set. But then we do it over, we take it over all of the P's, all of that are in the name. So these would be the conditions, yeah? It'd be the condition and the name.
Yeah, that's what I'm trying to understand. Like in that simple drawing you made, like we had a post set here.
Yeah.
Sorry. Why isn't this okay? Sure. And then you drew on top of it the two sets like these, right? We had this. This at the bottom is the post set.
Yeah. So on the bottom is P.
Yeah. So P is the blue thing here. Is one of these, like P, right? And the names are actually here. Okay.
No, because the pre-sheaf comes with the sigma to the PSH. So the pre-sheaf is different from the name. Every name yields a pre-sheaf. And the pre-sheaf contains basically 1 if you're smaller than the name, than the current point in the post set you're at, and empty otherwise. So it's like seems like an ideal, or where it's I don't know if we can draw it here. Yeah, it's like everything. If P is here, then my pre-sheaf is this thing, PSH, which is equal to 1 for everything that's less than P. Well, I'm off the page now, but everything less than P, and then 0 if I'm greater than or equal.
Well, that's
right.
It's sort of. It's not exactly. So that's what P to what this P pre-sheaf thing is. Okay?
Exactly. Yeah.
That's what this is.
Right.
The sigma is going to be a direct product of a bunch of them, which is basically just saying that it's basically a union. You can think of it, right? It's taking all of them it's just bundling them together, and it's taking all of them as one set for all of the P, tau, and sigma for all of the P and P. Right?
Okay, so there's many of these per name. Is that right? Like, is there many of these?
Yeah, it's gonna be for each time you have in the name sigma, each time you have a P come up. So for each element of the name, because the names are ordered, right, such that one of its elements is itself a name, so it has this like inductive structure on it. So I think the point of this is it takes this basic object, which is just a map that's gonna, it's like a it's like, what's it called when you use in physics and things, kind of like the I'm forgetting off the top of my head, or like an indicator function, right? That's just going to be something for one value and then 0 otherwise. So here it's all this pre-sheaf is doing, right? All it's doing is it's saying either something is greater than or equal to, something is less than, in this case, less than or equal to, you're plugging Q into it. So everything that is less than it will have 0. So it's defining basically the down set
Yeah, the down set.
Yeah, so you're taking a union of the down sets for each one of the elements inside the name itself. So I think the idea of what this is doing is it's at least once you take this relation afterwards, what it's doing is it's recreating the like inductive structure of the name, but constructively. I don't know if this makes sense, because each one of these p to the pre-sheaves is just like your basic canonical like indicator function. It's like the unique, something like the whatever, or unique up to one other function that whatever uniquely picks out this point p. Yeah. And you glue a bunch of them together. But then after the fact, you always have to, because you just take these together, you have to glue them back in order to actually get a proper sheaf rather than the pre-sheaf, to make sure that they glue together properly. Yeah, I don't know if I can quite justify all the details and all of this stuff, but I think that's the idea.
Why is T different? What again? P is, what is T again?
So T here, right? There should be the name and the condition, right?
Okay, so
the name is another name. Yeah, the name is another name, and the condition is an ordinal.
Yeah.
So here tau is an ordinal, right? So this is saying, right? So I'm going to say p tau is equivalent to p prime tau prime at level q. So noticing that like this forcing is always conditioned on some level of the post set, meaning that it's contextual to that level. And you glue them together when at q they're equal, but they might not always be equal, these ordinals, right?
Yeah.
Yeah, John, did you have a question too?
Yeah, you, just about the difference between the pre-sheaf and the sheaf, because you said that sheaf requires like gluing back together. Does that mean that pre-sheafs are often the double negative topology you brought up earlier? Are those kind of equivalent, or is that a different kind of stage?
Yeah, kind of. So the I have a little bit of thing on this later, but what the double negation topology does is it takes you from a classical world to an intuitionistic one, and this is the situation in which most of like the constructive forcing happens. So usually you take some classical model, you do this double negation topology on it, which kind of changes the structure of the space. It makes it into an intuitionistic. It allows you to look at a much larger set of models for the space. And then you can force something on that set of models such that when you glue everything back with a filter, it's going to preserve the force. And that's like the sort of what is in common with all of the force or a lot of the forcing strategies, especially with like the Cohen forcing and other forcing of whatever infinite sizes and whatnot. So it's almost like the other side of the coin of the generic filters is the double negation. But one I think really good or an interesting thing about the double negation topology specifically is, I believe I think this only is true strictly in classical models, but in classical models, at least it's equivalent to the dense topology, which basically is saying any set that's open is one that's going to be dense within it. So then as long as something can be true like almost everywhere, then you can force it to be true in the whole thing. So that's kind of a little bit of the relation between them. I think they're not strictly equivalent when you're in an intuitionistic world, but I don't know off the top of my head. Yeah. double negation will come up again. And Levere has written a lot. That's like a lot of what, I don't know if you know about his whole project to like, I think this is from a while ago. I don't think he's still working on it, but he like has this like formalization of Hegel's science of logic with category theory. And I know the double negation topology has a very crucial role in that as well.
Cool. Yeah, that really helps. Thanks.
Yeah. Let's see what that takes. Okay. We can go through a little more of this stuff, but we can always go back there. And I think we have more to cover from Rezo's presentation later as well. So I want to talk about a little bit about what's called the extensional property of truth in Sheaves structures. So this is what I was talking about before, how we're going to say that something is true, not necessarily if it's just true at that point, but if it's true in a neighborhood containing that point. And basically, as long as we are precise with how we construct truth in neighborhoods in a consistent way, it ends up being okay. Like it seems like this would be kind of a shady way to go about this. But it ends up working in a very natural way. So we think of sheaves of structures as being formed by variable objects, which vary or change over a structure of states of knowledge, right? So here, the states of knowledge would be the structure itself, right? So it's the mathematical structure. So like a sheaf of structures, for example, could literally be the structures, can be groups, it can be rings, it can be whatever. It's a general enough language to include just about all of mathematics that can be modeled within it. So we're going to say that a proposition is true about an object. An object here is going to be a section of the sheaf. If it's true in an extension, aka a neighborhood in which the object lies. So then formulated this way, it's not only global properties you can learn about from the topological perspective, like the classic example of like topological knowledge or something like the hole, or like a hole in the space. Like when you look at a donut and we look at it has the notion that it has one, I guess, two-dimensional hole that comes from the algebraic topology of the space, and it's an invariant that you can actually pick out and construct. But it's not just global properties, but also local properties, right? That we'll be able to get out. So I think this fuzzy way of conceiving of objects is more natural in the sense of kind of aligning with our phenomenological intuitions, and more general in the sense of describing more general structures because it's in an intuitionistic space rather than a classical one, and includes all of classical set theory as a subcase. Rather than, and I think it's slightly less essentialistic, and the like purely set theoretic perspective is very concerned always with what like absolute composition of something is, which I think, especially when we talk about things as not just like points, but as parts. So when we want to talk about the composition of something, what we're doing is not necessarily naming all the points of it, but most of the time it's something like naming the parts of it in such a way that it covers the thing, right? In such a way that it can fully describe the thing. So this is a much more like fuzzy way. There's a lot more ways you can slice it up and talk about it in a coherent way than just these are the things that make it up, or these are the points of the space. So using this idea, we can think of a topological valuation, aka like a measure on truth almost, for a sheaf of structures that is directly gives intuitionistic truth values from propositions, right? Okay, so it's pretty simple. Basically, we take for any set of sections, the sections are the objects that we're going to work on. Sections of some sheaf. Actually, I always thought this was A. I don't know if Dennis knows. Or this was a U, but turns out this is an A.
Oh wow, really?
Unrelated, yeah. I was trying to figure out how to find the same font, but this is an A in some weird LaTeX font. But so we have sections, which we can think of as observers or objects on a sheaf defined on an open subset U, okay? So then the truth proposition of some proposition phi, the truth value of a proposition phi in the subset U, we're going to define simply as the set of points in U such that on the node X, the proposition is forced. So it's going to be the nodes X such that the sheaf forces this on it. So basically, it's just taking all of the points in the base space that when we look above them, our proposition will be verified. So in this case, right, the bigger the set is, the sort of more true it is. And in fact, we're going to end up saying that this proposition, right, is properly true or forced on the entire set if and only if this set itself is the entire set. So it's kind of like a weird self-referential thing, but it does work. So we use this to define this topological evaluation, right? So we can get from formulas, right? So from the language of the space to actually on each set U get a set which maps its truth values in some way. And when we remember things about the subobject classifier, we'll see that this is literally mapping directly into the subobject classifier into the space. And all that stuff with BedU is compatible here.
Yeah, I just want to jump in and say that I think
Yeah,
this slide and maybe like one other slide, I think are the most important slides in the whole presentation, because I think for me, it clarified an idea about the degrees in BedU and the transcendental, which is that degrees not only describe a magnitude of truth, which is how we intuitively think of it. It's like, how true is it? Like not true at all to totally true. And there's some in-between values that we don't really know how to understand or intuitively grasp. But now I think the right way to think about degrees are as where something is true, right? If a thing is maximally true, it's true everywhere. And if the thing is not true at all, obviously it's true nowhere. But in between, there are as many possible ways you can slice up the space where the thing is true. So it actually has, it's much more spatial, and it also, in my mind, connected the relation between points on the one hand and truth on the other, right? They're inherently part of the same story. So I think that's going forward, just like keep that in mind, that a degree, to say like the degree of existence or the degree of identity between two things is like P, where P is something between maximal and minimal. You're actually saying it's true in some places and not in other places. And then you have this order relation between degrees where, well, if it's true in this place, it must be true in this other larger space, right? Or sorry, smaller space, all the way to, I guess the order really can be either way, but you can infer like if something is true in this region, like if it's raining in this city, then it must be raining in this neighborhood, this suburb or whatever, or this part of the city is also raining. That's the power of, I think, all this stuff.
Yeah. Cool. I think this next slide actually has some of the other good stuff. Yeah. Okay. So here, this is kind of divided into two sections. I should have put, I guess, a line underneath this bottom, formula in the middle. But this first half is basically extending the idea of the valuation of logical propositions. Thank you. The valuation of logical propositions, right? So we can define the truth value of equality as the sets where were here, right? These are sections where their individual values on that section are equal. So this could be maybe if we think about maybe our sheaf of structures is like the multiverse or whatever, right? We're in an Everettian world. So this equality could be like between two different observers who at some point are in different worlds and at some point are in the same world. This is sort of like the place in which they agreed, something like that. And in the same way, you can do this for a lot of things. You can spatially describe how the logical relations work contextually, right? So all of this is always contextual in some set U. So it's not like this is giving like the whatever universal truth value for all sets or anything like that for any of these propositions, but it's saying how true these propositions are over this specific set. And it follows here, right, that we say that, and this is the moving from the point perspective to the more like open set perspective, that the sheaf of structures U forces a proposition on an entire open set, or models a proposition on an entire open set, if and only if the valuation of the proposition on that open set is the entire thing itself. So this conforms, right, with this Bedouin idea of this is the top element. If we think of U itself as its own Hating algebra, as having its own transcendental, right? That's the topology essentially. So it's always localized to something. This is the maximal element it could possibly be within the subset. And it's important that it's always relational to where it's coming from. So
yeah, I just think that is really mind-blowing. That if I ask you in this frame of thinking, if I ask you a question like, is it raining? You don't tell me yes or no, you tell me the places where it's raining. Right? So your answer is always a space. That's the, I think it's very interesting.
Yeah. And the point is, in order to get, right, this yes or no from the space, it ultimately ends up becoming some choice. And this is what basically the filter of it, a filter on the spaces. It's going to end up being some choice of yes or no for each one of these things. So it's either yes, this set on which it's true is big enough such that we can just sort of say that it's true, right? That it generalizes enough. This is almost like something like, I guess, almost like what the process of science is, right? You can say that something, some scientific proposition in like the traditional perspective, that some scientific proposition is true once whatever certain amount of repeatable experiments can make the same prediction over and over. So it's always going to be some amount of truth, right? It's a truth in that case that is conditioned on all the experiments that have been done on that specific proposition in that point of view. So I think in this context, right, this is a really amazing point, I guess, theorem or corollary of this perspective, is that the law of the excluded middle, right, which is what's going to force something to be classical here, is forced on a node X, right? So in a specific context, in a sheaf of structures, if and only if there's a neighborhood U of X, so there's some neighborhood around this point in the space, such that the inverse of the sheaf, right? So this is taking the stalk. So this is taking all of the structures on top of this open set that's containing this point. is a Hausdorff topological space. So this is something I should probably define. Maybe, yeah, I meant to define it, I think. But the idea, annotate here. The idea of a Hausdorff topological space, if you guys have not seen it before, it's basically, we're gonna say a space is Hausdorff if and only if for any 2 points, okay? So for any x and for any y, it's Hausdorff if and only if I can always draw some open set around each of them that don't intersect, right? So I can separate them by open sets. Yeah. If on the other hand, I have something like there is this one construction, I forget the name of it. It's basically taking just the real line, and it takes 2 copies of it, and it glues it everywhere, right? Except for 0. Except for at 0. I'm gonna not glue it here, but glue it everywhere else. So this is actually a coherent thing you can do. And you can define the topology in a way that makes sense. But it ends up being not a Hausdorff space because, right, you end up, the resulting thing, so this is the covering of it. This is actually also, actually, I don't think in this case it's a sheet, but you end up getting this second point here, which at the same time, right, is in these open sets, but these 2 points are inseparable. And there's a whole bunch of examples, but a non-Hausdorff space is like very unintuitive. It's hard to imagine what it is, but you can pretty quickly get some examples. If you want to,
just to go back then to the statement, the law of excludability is forced in no x in the sheaf of structures, if and only if there is a neighborhood U of x such that.
Let's maybe draw a picture. So let's say we'll have, so we'll have some base space here. Okay, be a topological space. So we're imagining it some kind of surface. Okay, so we say that at some node x, right? So above x, this is here, right? This is P inverse. So remember, this is the kind of topological way of thinking of it.
The inverse is sending us back to the.
It's sending us back to the structure that's on top of it, I guess. Yeah. So above P, whether there's some structure, and above, this is the same above every single other point. And they all glue in some way. So it's saying that the law of the excluded middle holds if and only if. And remember, when I have these structures, right, these don't have to look like fibers, right? They can be glued together here. There can be weird stuff going on. There's probably, in fact, weird stuff going on, okay? So it's saying I can pick some set, and it's always important that there's some set, right? It doesn't matter how small it is, as long as there's something that is we consider local around it, such that when I raise it and I go up, so that's going to be looking at these things, looking at this entire space. So it says that the law of the excluded middle is forced in X. So X is going to be classical if and only if the structures, there's some open set with structures around it, such that this is Hausdorff.
Yeah, it being Hausdorff means that it kind of mimics the property of being closed, right?
No.
Yeah,
Hausdorff means that
you can distinguish everything at some point, right?
That's right.
Yeah, pulled out.
Yeah, it means that any
some kind of way.
Any 2 points can be distinguished in some way.
Yeah, it's counterintuitive because we think of distinguishing as forming a border. So but if for some reason in topology you can distinguish 2 points with open sets, that don't have any border.
Yeah, I'm just trying to see because there is a connection between this junction in the Hausdorff space and this junction in the law of excluded middle, right?
Yes.
So it seems like the Hausdorff property there is doing something like some topological interpretation of something that is logically classical.
Mm-hmm.
I mean, it almost seems like
Yeah.
it mimics the axiom of choice in a weird kind of way, right? Because it gives you the ability to reach in and pull out one thing, where like what non-Hausdorff essentially means is like there's at least one
yeah.
pair in there that you can't separate out, right? Like you can't actually pull out just one.
Not exactly, because it doesn't explicitly give you, right? So like the axiom of choice is basically saying for any set, I can pick one thing, or sorry, for any set of non-empty sets, I can pick one thing from each one. That's the axiom of choice. This is saying for any 2 points, so it doesn't matter, it's an infinite set, I can pick open sets around each one of them. So that's conditioned on the topology, right? So that there exists 2 open sets within the topology such that their intersection is empty, right? And they surround each of the points individually. So yeah, it means, I like to think of the topology as I think I mentioned this before, is it's like the space, it's almost like a space of the states of knowledge. It's like what is sayable within the global space. But like normally, I mean, you can't always, especially when we think of propositions as subsets, right? We don't immediately have access to every single proposition that could, or we don't have access to propositions that can, at least maybe not yet, that can cut our space in any way we want. Basically, because of Gödel, there's always going to be more propositions from this perspective that can be formed from the space that our language will not be sufficient to answer.
Yeah, I was just going to add in that this picture, I mean, this is how I'm picturing it, that if you think about the lattice of propositions again, if you affirm one proposition, it excludes a bunch of other propositions, and it makes other propositions possible. So law of excluded middle would look something like, if you had a node where both P and not P were possible, this is your sorry, this is like 2 different propositions, right? P and not P. They're in the same state of knowledge, in the sense of they're both still possible. You haven't proven one or the other. Now, the law of excluded middle says if you were to prove one, you've excluded the other. So taking one path means you can't take the other path. Right? So there's there's 2 open sets that distinguish the 2 points, and you can only choose one. And if you choose one, it excludes the other. But if you don't have law of excluded middle, like proving P doesn't necessarily imply you've canceled out. Sorry, proving not P doesn't necessarily mean you've also forced P. Right? It maybe down the road you may also find out you can't force P.
Yeah. So if you don't have, that's a good way of thinking. If you don't have,
and this looks very, very like very much like the Hausdorff thing, right? I mean, if I have this,
I think it is literally.
I can actually make these 2 disjunct things. Yes. No, I can see now that it does capture. It captures in a parts and wholes kind of a topological way, an aspect of what the excluded middle implies for propositions, right? That you must be able to separate them in the P and not P in a disjunct way.
Yeah. So this, I mean, the reason I include this specifically, this is like one of the most explicit connections between the geometry and the logic. So we see that a topological property, right, of being Hausdorff, of being able to separate points, ends up conditioning the logic of the space.
That's so crazy.
Yeah. Another crazy thing that we mentioned before, but that a trivial case, right, is if the node X is either an isolate point or if the entire X is just one point. So basically what this is saying is that just, okay, this is the entire category. Sheaves on top of this, generalize any set we want. So if we have this, so if we have a sheaf, which is, you can take any set, and this is gonna model any, basically one set with any number of elements. By doing whatever, a sheaf of structures over this. The idea is that the structure is the generator, basically. This is essentially, right, like the empty set that in set theory, everything is built on around. And in this case, right, if we're only doing it on one thing, we get exactly the classical case, which is that the sheaf of structures forces a proposition if and only if at the node X, it forces the proposition. So this like atomizes it, and this makes it into the classical case. So then now this doesn't depend at all on how you move within the space. It's not conditioned on that. It's just whether it applies at the point or not. And this, right, these structures on top of this space, this is all of set theory. This is all of set theory down here. There you go, done. Set theory done. So
that
set theory
means like
is so basic.
If you like can somehow detect that a space is Hausdorff, you know that no matter where you're going to go in it, these statements are going to be true. Is that the?
If you can detect.
Like
yeah, but here this, but
it's
here
like
so
homogeneous somehow once you detect Hausdorff, right?
Yes. Yeah, it's it's if it's Hausdorff, it's classical. Yeah. And this is the space of sheafs of structures over a point. So this is for the global section. Oh, sorry, this is the fiber over the open set. Okay, let me clear these. Any questions? I guess it's already getting kind of, I don't know if we want to continue or if we want to wrap up, because I think this is around where it starts to get really crazy. So if we really wanted to,
yeah, we can continue next week if you guys. I mean, I think
we might want to. See.
What do you guys have still for this? Just so we can.
This is where the generic model stuff, and I had to kind of gloss over a lot of the details. This is, there you go.
I think we can use. I mean, I think we could try to combine for next week, like what's left in this presentation and what Reza wanted to talk about, which I think probably fits very well. And then just have a debate.
We can do that and start at actually we can start on generic models.
Yeah.
There's a couple things here I wanna tweak a little bit anyways. So
yeah, no, this was so clarifying, so many.
Hopefully this was a little good.
Yeah, this was great, Josh. That made sense of so many different things.
Yeah, hopefully sheaves make a little bit of sense. They did not, even before now, I was like, what are these? And now I kind of understand them a little bit. So
no, this was really helpful and
continuous
and might I say really pretty presentation.
Yeah, found some good pictures for it. Cool. Okay. We can end there
great.
then.
No, okay. So I think there's a lot to work with. I'm gonna listen to it again for next week, just so we can kind of also force as much as we can kind of all this material into the kind of unsaid stuff in logics of worlds. I saw that you guys are already gonna go into this anyway, but I think it's a good idea to have this in mind for next week, so we get to cover that as well.
Cool.
Yeah.
But also, guys, you see, I've had cats climbing me this whole time at the end.
Pat wants to learn what a generic model is as well.
Yeah, true.
I was gonna say, yeah. So I also can talk about the exchange sheaf next time. There's some slides on that, and I mean, the crazy thing is this. My mind is still blown by this, like the spatial interpretation of things. But I think that actually clarifies like what we were trying to do in the primer with this exchange sheaf a bit further. So hopefully we can tie it back to that and make the primer a little bit clearer.
Yeah, hopefully I can go through. I want to maybe try to see if I can clarify a little bit some of the stuff on specifically on the forcing stuff. It's very hard to, I guess, conceptualize, because it feels very recursive, and it kind of is by how it's constructed. It's constructed in a very similar way that the cumulative hierarchy of sets is constructed. In fact, there ends up being a cumulative hierarchy here, which is like a more complicated hierarchy, basically.
Yeah, this is something we were talking to Reza last time, like right at the ending of it, that it's interesting that Cohen it's not like you cannot make and actually this goes back to something that I'm more and more convinced, like in post-war philosophy, usually you have two fields: the poor taste philosophers who are all for the correspondence theory of truth, and the good taste revolutionary philosophers who say that truth has nothing to do with that. And like Lacan and Derrida and these guys saying like, well, the idea of corresponding, truth being like the correspondence of some proposition and a state of affairs, that's like so outdated. And what are your criteria for that correspondence? And they criticize this and they propose something else, right? And more I'm realizing that Badiou is actually absolutely classical. I mean, he's all for this correspondence theory. It's just that the reference of these propositions, he's a materialist. You can actually construct the reference. And I think that you can get a feel for this specific strategy, which is not with a move from Gödel to Cohen, because it's not like he abandoned the idea of benefiting from a cumulative hierarchy and the way that this guarantees some sort of coherent structure on your propositions. He just doesn't construct it on these, let's say, simple statements from these definable propositions from the get-go. So it's not like you abandon the idea of correspondence. You just show that you don't need to kind of apply it in the, let's say, very, very simplifying, saying like kind of this more intuitive way, right? That, well, I can make simple statements about what's up in front of me. All complicated statements are somehow derived from the simple statements. You can still have a theory of truth that does keep this idea of correspondence to some level. You just can be very, very clever on what it's referring to and how you construct this sort of recursive building blocks, right? Yeah,
I think the point of, yes, you're right about the correspondence, but it's always, what it's referring to, right, is always some substructure topology, which is like the main point here.
Yeah.
That choice is always like a constructive choice. Like you have to sort of build it with the language or whatever.
Yeah.
It's never like, you never have access to everything all at once.
Yeah.
And in order to actually name things, it takes work to build it out. And then after the fact, you can see, oh yeah, it was just a correspondence. I think that's kind of the
no, I agree with you. And I don't even think that you would like to put him in this field, because in so many ways he's saying he's doing something else. And I think that it is a fundamentally different approach, but it's not this romantic other thing.
Yeah.
It's much more playing the same field and then showing that there's more to it than it seems. Then, right, for example, rather than names being useful because they're naming previous names and the previous names are naming previous names that are actually naming the empty set. Therefore, you get this perfect kind of cumulative hierarchy. You can name something at a rank so that it's actually capturing information about the ordering, not so much about what the fuck is there, right? That's still in the same ballpark of the strategies. It's much closer to this classical approach. It just takes you somewhere else, but it's I don't know. It's just something that by studying this a bit more now, I see a bit more clearly. Like I feel like this is actually a big kind of a big part of how counterintuitive his approach is, because he wants to arrive at something that very radical continental philosophers want to say, something like truth is not the same as knowledge, or it's not the same as something just being veridical. And he says, okay, you're right. That's a property of truth I want to preserve. But you guys want to let go of a lot of more classical tools of, semantics and understanding of truth. You don't need to let those things go to keep that property as a verifiable thing at the end, right? It's really weird.
Yeah, but it also, I think the important thing is it always requires, I think, the faith that the world is infinite in and of itself, right? Which I don't think very many people say, but I think when you really work through it, it becomes pretty natural.
Yeah, I mean, this is something also changed my mind a bit. Like in the beginning, I used to think that it meant that Badiou is claiming that there are, that his strong statement is there are infinitely many things in the world. But I think that his strong statement is properties of the world that you see if you're engaged in struggles, if you're interested in science, so on, they are better, they're more natural if you assume the world to be infinite. Like they become tractable. So you can take this as a sort of abductive, pragmatic reasoning. You don't need to take it as a kind of metaphysical claim. You can simply say, like, it's weird how some stuff that you know and see empirically, if you're engaged in certain things, they look like impossible enigmas if you assume the world to be finite, and they look very natural and thinkable if you assume the world to be infinite. Like, so the strong claim is about the existence of these procedures, and the infinity of the world is, well, something that looks quite true if those things exist, rather than the inverse, right? I need to convince you that the world is infinite, and therefore you will accept that those procedures exist. That's not really how I think he operates.
Yeah, I think you also see the infinite in the world, and one possibility, right? When we can talk about like possible worlds as being, or at least are like close enough as being close enough to the world. So, in the sense that we can say those exist, right? Then there's already infinitely many things that could be different. But also, when we think of objects as parts in and of themselves, within an open set, and like explicit instantiations of them as like a point in that set, then you can like continuously vary like the properties of the objects in infinite ways and still stay within the boundaries.
I have the impression that this discussion on infinity and finitude of the world, it's probably why Kripke is not Badiou. Like, being an analytic philosopher, much more classic in a way, surely not interested in like making bold statements about the actual world. I mean, he prefers to associate infinity to counterfactual space, right? And Badiou associates infinity to actual space.
Yeah.
And I think that might be the case why for him, like, possible worlds are just, okay, it's this other thing, right? And for Badiou, assuming that the world is infinite actually makes this possible option. Like, the interesting part of it is that it is actual, or possibly actual, not that it's actually possible, right? It's different. But it's an interesting comparison. I haven't seen anything written on the two. It'd be interesting.
Okay.
Guys, thank you so much, man.
I'll spend another week thinking about this stuff.
Yeah.
Thanks,
hopefully
guys.
have better thoughts about it. Yeah.
See you guys next week.
All right.
All right.
See y'all.
See y'all.
Bye.